Yeah, so I'm so close to finishing. You know, at one time at this weekend, I was just like grading. I was just almost like, F it. I'm just gonna like give you guys the rest of the questions points, but no, I'm almost done and I'm gonna do it right. So I'll get those to you relatively soon. It's also because I have like my own things like research and I like have to like keep up with that with my advisor. And so yeah. Don't worry. It's I'm not like putting it in the back burner or anything like that. Yeah, I pretty much spent all of Saturday and Sunday doing it. It's just that it takes time to read and like assign these points and all that stuff. Okay, so any other questions in the meantime? Okay. Uh, all right. So last time we were talking about. Oh yeah, that's just the notes at the moment, but cause I still have to figure out how to like download the like it says that like I can download or access the record somewhere, and I uh, just haven't figured out like how to do it or had too much time already to figure it out. But I will at some point. Just keep asking me, and so I can remind you can keep reminding me. Okay, so last time we talked about the concept of linear combinations, right? So I already introduced that concept earlier in the course, but I introduced it again. Remember, linear combinations is just if you have a set of vectors, you combine them. So here, let's see, like, like yeah, so you combine them to make them look like this, right? And then a vector v is a linear combination of another set of vectors that v can be written in this way, right? And then we talked about something called the span, right? The span being the set of all these such linear combinations, right? So you combine them and you combine them by adding and multiplying scalars. You get all the possible combinations, put them in a set, and that is called the span of a set of vector sets, right? Um, then I talked about how it looks, right? So we took the span of the vector 1, 0, right? So right there, right? And then the set of vectors that all linear combinations of the vector 1, 0 was giving me the line on the x-axis, right? So the span is, you can think of it as like a line. And then I'm going to give you more vectors and see what they look like in higher dimensions. But after that, then I said, okay, we have this thing called the span, all possible linear combinations, right? So what happens if I give you a set of vectors, right? And then you take all possible linear combinations of them. And then you inspect this set that I gave you, right? And you see that all the vectors in this new span is all the vectors are in my vector space. So what happens then? Well, in that case, you say that S spans V. And I think I can write it a little bit more precise. We actually say that span of S is equal to V. Okay. So that means no matter what the vector space I give you, I give you the vector space. If I know that S spans the entire vector space, I can pick out a vector from V and always write it as a linear combination of the vectors in S. That's what that means. Okay. Then I talked a little bit more about what happens if I take the span of this, right? So you see, if I take the span of these three vectors, it actually it gives me the entire space. And if I take the span of, say, these vectors, it gives me that plane right there. So always think of these as like a line, a plane, or like 3D space or higher dimension. You call them hyperplanes, but higher dimensional like planes, right? Um, let's see. And then we moved on from there to another example, right? So I talked about, okay, so remember the idea of vectors is no longer just arrows in Rn. We can think of them as polynomials. We can think of them as matrices, and we still have the same notion, right? So we talked about that right now. So now we're gonna move on and do more examples. I'm not just gonna like leave it there, but so the next thing is that uh, is that that the set span of S is not just a set; it's actually a subspace. So what does that mean? Well, it has the structure of vector space as well. It isn't just some random set anymore. It has a structure of vector space. And this is going to be important because then we'll talk about bases and dimension later. Okay. All right. So now we've built up the notion of span, what it is, how you can visualize it, and what it means like in terms of the vectors like in it, right? Next thing we're going to talk about is something called linear dependence and independence. So we talked about linear combinations. So now let's talk about something called linear independence. So let's see, let's do this definition. So a set S of, say, vectors u1 through un is, or I guess in a vector space, v plus dot is linearly independent if the equation, or yeah, the equation C1 U1 plus all the way to Cn Un is equal to 0 has only the trivial solution. Or in other words, C1 has to equal C2, has to equal C3, all the way to Cn, and the only solution that will solve this is if every constant is 0. That is the only solution that will solve it, okay? I mean, that's the only thing that will solve this vector equation. If this is true, then the set of vectors is called linearly independent, okay? And again, the definition might seem, kind of weird, but I'll illustrate what it means, but also what the implications are. But anyway, so otherwise, it's called linearly dependent. Okay. All right. So let's see. So, question. If I give you a set of vectors, concrete vectors, how do I solve it? How do I make sure that this only has either the trivial solution or something else? Like, how can you solve it? If I give you the vectors, like say 2, 3, 4, 5, I don't know, and what would you do to solve it? Or just like solve this equation? So, question: how check linear independence? Well, the answer is in Rn, set up a augmented matrix, right? Right. You just put the vectors in a matrix with an augmented form with zeros on the right hand side. RREF it, and okay, so if it has only the trivial solution, what should that reduce down to? If you RREF this matrix. So remember, the only you can translate this in other words, has only the trivial solution, meaning the only part means that it's unique, right? It only has one solution. So in order for it to have one solution, what should it reduce down to? The identity, right? So if the RREF is identity, your vectors are, I'm going to abbreviate it now, linearly independent. Okay, in other vector spaces, other than Rn, so you can't. So in other vector spaces, like the space of polynomials, you can't just put them in a matrix and try to RREF it. So in that case, you have to actually solve U1 sorry, C1 U1 UN equals 0. Actually, you're going to have to actually use this form. You can't use the augmented matrix. You have to. So if you have 0 equals 0, that means one of your rows is all zeros, which means that you have a free variable, which means you have infinite solutions. So in that case, you would have linearly dependent. So you have to have it to. So basically, it has to RREF to this. So if here's your like zeros, right? You have to have like this. So it has to look like this, right? And maybe I should move this somewhere over here. Hold on. So cut this. Move this in. So there. Much better. Whatever. I think that's fine. So yeah. Okay. So let's do some examples. What is it? Okay. So example, what example is this? 4.44. 4.44. Let S equal the set of, I don't know, these vectors right here. 1, 2, 3. 0, 1, 2. Negative 2, 0, 1. Is S linearly independent? In the vector space R3 with your standard operations? Well, solution in Rn, if when you have your standard vector space in Rn, all you have to do is just take these vectors right? So setting up augmented matrix, all you have to do is then check 1, 2, 3, 0, 1, 2, minus 2, 0, 1, and then where your
This
zero
video
goes,
is proud.
right? So RREF this. So once you RREF this, what you should get is 1, 0, 0, 0, 1, 0, 0, 0, 1. So what does this mean? Well, it means that C1 has to equal 0, C2 has to equal 0, and C3 has to equal 0. So the set is linearly independent, and your vector space R3 with the standard operations. So if you have this situation, it's linearly independent, okay? So, oh yeah, by the way, so you'll never have an inconsistent system with this, right? Because if you set it up with zeros on the other side, you're never going to get the situation where you get 0 equals 1, right? So you're only going to have two situations. It's either going to be identity, unique solutions, or you're going to have one row be completely zeros. So if this doesn't happen where you reduce it down to the identity, then you say your set S is linearly dependent. Okay, so in this case it's linearly independent. Okay. All right. So this is how you do it with normal vector. Well, in what you know, right? So what happens if you take maybe the vector space of polynomials of most degree 2? Well, now you can't use the same trick anymore, right? So let's actually look at an example and see how we can do this. So let's do example 4.5. Oh, 4, 5. So let's say S equal the set 1 plus x minus 2x squared, 2 plus 5x minus x squared, and then x plus x squared. Okay, so remember, now we're considering these things to be my vectors. So you can consider this one to be like u1, this one to be u2, and u3. Well, they're vectors in the space of in the vector space of polynomials. So now the question is S linearly independent in the vector space P2 with your standard operations of, adding functions and all that stuff, right? Okay, so in this one, we can use the same trick. However, we can refer back to what it means to be linearly independent. So let us solve C1, U1 plus C2, U2 plus C3, U3. And this equals 0. Okay, so now replace my my U1s and U2s with and U3 with the polynomials. So this would be so replacing 1 plus x minus 2x squared plus C2 2 plus 5x minus x squared plus C3, and this is going to be x plus x squared, and this equals 0. Okay, so now what do? Well, you might think you can try to solve for x, but you're not solving for x. You're going to remember your goal is to show either C1, C2, C3 is all zeros, have to be all zeros, or one of them, if it's not all zeros, then they're linearly independent, right? But so that's your goal, right? You're trying to solve for what C is, or C1, C2, C3. So now let us solve for C1, C2, and C3, okay? All right, so what you have to do for this one, so there's a nice little result that the book skips over, but polynomials, as you know, are, well, maybe you might not know, but they're unique. What does that mean? If you have a polynomial, say 2x squared plus 5x minus 2, is there any other way to write that polynomial or a quadratic with different constants and still be the same polynomial? No, right? There's absolutely, that's what it means by unique. You only have one representation for the polynomial itself. So that in itself, what it means is that if you have two polynomials, say, so let's just say, so now recall that if we have, let's say, ax squared plus bx plus c, and say we had abcd dx squared plus ex plus f, and so if satisfy ax squared plus bx plus c is equal to dx squared plus ex plus f, then this has to mean that a equals d, b equals e, and c equals f. You can actually show, you can, how you prove this like rigorously is using the vector space properties, but we're not going to do that. But this is what we're going to use this fact to help us solve our C's, okay? So using this fact, let us solve our problem. Okay, so let me go get this thing again. Okay, so let's distribute everything, right? So I'm gonna distribute my C's. Let's see, let's see. This is gonna be a pain. Okay, hold on. So okay, whatever. Let's just do it. 2c1 x squared plus 2c2 plus 5c2 minus x minus c2x squared. Okay. So you see what I'm doing? I'm just distributing, right? Oops, not what I wanted. Yeah, so we're distributing the c, so now I'm going to have plus c3x plus c3x squared equals 0. Okay. I mean, there's one or two ways to do this, but what I'm going to do is I'm going to gather all the like terms. So everything that has an x squared, right? Everything that has an x, and everything that has just a constant c. That's it. Okay. Yeah, c1, c2. Yeah. Oh wait, I'm looking at the wrong one. Yeah. Okay. So yeah, perfect. Okay. Now gather all of them and factor out an x squared. Right? So the x squared, so what I'm going to have for that one in front is, so if I factor that out, I'm going to have a c3 minus c2, right? So, and then, oh, I forgot the other one, plus c3, yeah, so c3 minus c2 minus this over. And then with the c1, you have minus 2c1, right? Okay. Now gather all the terms with the x. So if I do all those, so I'm just gonna have a C1 plus 2C2, and that's it. And then all the terms with the orange thing. So you're gonna have a C1 plus 5C2 plus C3, and all of this equals 0, right? So yes. All right. Oh yeah. Then which should the x? My bad. Yeah. Yeah. That's a good thing we have this good notes thing, right? Yeah, this is what you mean, right? Yeah. Yeah. So see, easy fix. Okay. 5C2. Oh, for the x, I think I fixed it. Is that fine? Yeah. So yeah, we fixed it. We fixed it. Okay, perfect. Okay. Now let's go back and read and look at this result. So since the left-hand side is that polynomial and the right-hand side is the zero polynomial, what does each one of these have to equal? 0, right? Yeah, exactly. So we equate them all to 0. So, equating all coefficients to 0. Okay, so we're gonna have C1 plus C2 equals 0. We're gonna have C1 plus 5C2 plus C3 equals 0. Minus C1 minus C2 plus C3 equals 0. Okay, now we have a system of equations again. So now this is brought back to R. So now we can use augmented form in this case. So now using yes, you are correct. Yes, I think that's yeah, that should be fine. So now let's see. Okay, well, I'm gonna have a 1 minus 2 here. I'm gonna have a 2, a 5, a -1 here, a 0, a 1, and a 1. And then 0, 0, 0. RREF it. And this will give me 1, 2, 0, 0, 0, 1, 1/3, 0, 0, 0, 0. Now that we found our C's, is that set of vectors linearly independent or dependent? Yeah, so they're dependent now, right? So this didn't reduce down to the identity. So these are linearly dependent. Okay. Let's see what we have. Perfect. So I mean, you can. So basically, you do this like process with vector spaces other than Rn, right? You might have to use properties of things in that vector space. Like if I were to do the matrices one, right? You would have to try to use the properties of matrices to try to get a system of equations out of the C's or something like that. And like how we did with the polynomials. Yeah, this is an example of the book. Yeah. This is I think it's example. I think page. Was it like 181, example 9. So this one should be the example. I mean, there's more examples that out there, but this is how you generally attack testing linearly independence or dependence. Okay. So the general rule of thumb is that this thing right here does not reduce down to the identity. So if it reduces to the identity, it's linearly independent, right? Because I mean, C1 equals C2, C1 equals 0, C2 equals 0, C3 equals 0, right? That means you only have the trivial solution. That's only if this reduces down to the identity. If it doesn't reduce to the identity, then it's linearly independent, okay? So that's how you distinguish from the two. Linearly independent reduces down to the identity, dependent does not, okay? Okay, so maybe so let's see what's maybe a good way to say it. Maybe you see it this way. So from here you can say that C1 equals minus 2C2. From here you get C2 equals 1/3 C3, and then C3 is free. So you have infinite solutions, and where is it? It contradicts the definition of linearly independent, only having trivial solutions. That's why it's also linearly independent. So we'll do more examples. I mean, this idea of linearly independent is not going to go away. So we'll still be doing more examples of it. So let's see. What's the next thing I want to talk about? Okay, so how about this? I was just wondering if I should mention it and mention this part, but maybe I don't think it's I need to mention it. Okay, so okay. Now question. Given a set S of vectors, suppose S was linearly dependent. Let's see. How can we change S to be linearly independent? Oh, and this is not a question mark. So okay, so now suppose I give you a set S, right? And you put it in your matrix, and you found that you didn't have the trivial solution only, right? You had infinite solutions. Now I told you, okay, is there anything you can do to modify this set S to make it linearly independent? The answer is yes. There is something you can do, and what you can do is take out one or take out the vectors that is making, in a sense, making S linearly dependent. If you can take those out, then you can create a new set, and that set would be linearly dependent. Okay, but I mean, so now okay, so how do you now check? How do you even like know which ones to take out? Well, this is how you can know which ones. So let's say theorem 4.4.2, I believe, right? I think it's 4.4.2. Yeah, it is. Perfect. So what does it say? Well, a set S, let's say you have U1, UN, and then you had this extra one, V1 in here. Or okay, so let's see, maybe I should write it a little bit better. Okay, maybe I can write it better. So let's just say you have the set. So it is linearly dependent if and only if at least one of the vectors can be written as a linear combination of the other vectors. Vectors in S. So let's just say you found out one of them, and you picked one of them, right? And then you found out it was written as a linear combination of the other. So remember, how did we do that? We just literally set up, you take that vector, and then the rest of the vectors, put them in augmented form, with that vector being on the right-hand side of the dotted line, and all the other ones on the left-hand side. If you REF it, and the system's consistent, then it's a linear combination of the others, right? If it's not, then it's not. But if you have this, then your set is linearly dependent, okay? And all you have to do at that point is then take out that vector that you can write it as a linear combination of the others, and what's remaining should be linearly independent. Now, there could be multiple ones in there that are linear combinations of others, so all you have to do is check which ones are linear combinations of the others and take all of those out, and then the remaining set is linearly independent, okay? Okay, so that's the idea for that. However, we can do something better than that, right? So, I mean, who under, I guess, who has time to really check each one, like, if they're linear combinations of the other vectors, right? What if I gave you like a set of, like, I don't know, 10 vectors? I mean, I'm not gonna try to check every single one of them, right? There is two more things you can do. And the last thing I show you, it's actually gonna be probably the easiest. And I don't think the book shows you it, but I'm gonna show you it. So one of them is, it is in the book. And so this is another theorem. So 4.4.3. Yeah, again. So basically what the theorem is going to say is that if you have two vectors and one is a scalar multiple of the other, then that set is linearly dependent. So all you have to do is really compare two vectors and see if one is a scalar multiple of the other. If it is, then take out that vector, and that's all you have to do. So two vectors, U and V, in a vector space B plus are linearly dependent if and only if one is a scalar multiple of another. Okay. So for example now, let's say I give you the set S to be 1, 0, 0, 0, 1, 0, and let's say 3, 0, 0. So right now, as it is, it's linearly, this set is linearly dependent. So which one can I take out, or which ones? I guess there's more than one choice in here. Which one can I take out to make this linearly dependent now? And by the way, the theorem statement is if and only if, so it's even stronger, right? So if you have one that's a scalar multiple of another, then it's linearly dependent. So it goes both directions, right? Okay. So now let's check on. So is this one? Are these two scalar multiples of each other? No. So that means that these two have to be linearly independent. Okay. What about these two? Yeah. So that means I can just pick one of these, take it out, and then the remaining thing is linearly independent. Okay. The last way that the book, I don't know if the book shows you or not, but I don't see it here, so I'm just going to assume it's not. So the last way is this. To check which vectors to remove is as follows. Say you had a set S of vectors, say U1, U2, and UN or whatever, and you wanted to see which one, and you found out that this thing wasn't linearly independent. Okay. And remember, how did you find out it was linearly independent? So one, set up the augmented form, at least an Rn, right? So this only works in Rn. So you have U1, U2, all the way to Un, and then you have your this, right? So you have a matrix whose columns are U1, U2, U3, right? If you RREF it, and let's say you got 1, 0, 0, 0, and you keep going until, I don't know, and then here, and so let's say this is part of it, right? And then the remaining stuff here is like some other gibberish that isn't, let's say, I don't know, some new ones, right? Some new stuff here, right? Then you have 0, 0, 0, whatever. So let's say your matrix reduced down to this thing, right? So part of the matrix has ones and then zeros in the rest of the column, and then part of it has like just not that, right? So basically like something like this. So if you go back to this guy, right? So you see the only one that satisfies that is well, okay, so maybe I should be a little more precise. Okay, so that isn't completely true. There's one. Okay, so say okay, better yet. Yeah, I can say it this way. Let's say you have like this part be like maybe ones here, and then all this other stuff is zeros, and then you had like non-zero stuff down here, and then all your rest of the stuff is non-zero, right? So stuff like this, right? And then I think it should be something more like, it can be like, I don't know, like one. these can be zeros as well. And then all this other stuff is gibberish. Okay. So I don't think I told you guys about what pivot columns are, but, or maybe I did. So you see how here, here's right here, the only part that's a diagonal is this part, and then everything else is zero. So everything that has a pivot column, meaning you have a leading one, and then everything else, you don't have a ones anywhere else. The vectors that are right here. So if you go back here, or I guess so. Yeah, I think it would have been better to illustrate with with an example instead of with this general form. So let me just finish this general form. But so let's say this part right here was like corresponded to this part right here, right? So wherever you see this happening, where you have pivot columns and where you have this like one stuff going along, and then zeros everywhere else, this stuff there is the linear independent vectors. The rest of it you can just take out. Okay. So if I go back to this example over here, this one right here that was horribly annotated, so save copy. So if I go to this one, so I got this one, and then the matrix was, the original matrix was this. Right, so this is what it RREF to. Right, so everywhere I see a one, a leading one, take those vectors right here. So those are the vectors I'm going to look at. Come on. Okay, whatever. Should have thought about that before I did that. So take those vectors, leave them be, and then just remove this last one right here. So this one just take out. And these remaining vectors are linear. So now these are linearly independent. Okay. So again, put the vectors in an augmented form, RREF. Look at what each all the leading ones. Take those vectors with the leading ones, keep them, and then the rest of them just throw them away. And those remaining ones are linearly independent. Okay. So this is probably the more efficient way if you're doing it RN, definitely. But yeah, so any questions for the last 2 minutes or so? Yeah, it has no leading. Well, not because it doesn't have a one. There's no leading one, right? So if it did, so let's just say it had this right here, then it would have a leading one. So that means that that third vector would also make this entire set linearly independent. But since this didn't have a leading one, yeah, you throw it away. Okay, so I think that finishes this section. We'll still be talking more about the span stuff. So next time, what's the next time? So next time we talk about something called a basis and the dimension. Yes. Of a vector space. So you guys know that R3, what kind of dimensions does it have? Well, in your mind, you just say it has 3 dimensions, right? R2 has 2 dimensions. Well, now we're actually going to discuss why we say those things have dimension 2, 3, 1, and that will be completely dependent on what we just talked about, like linearly independent stuff. But yeah, so yeah, I'm sending notes, but you guys are free to leave. I mean, you guys technically were.